Hi guys, a very good morning. We have very less number of people today. Issues. Let me share my screen. Right. So hope you remember what we saw last class. Right. We were talking about chemical properties, if you can remember. Right. We finished with preparations. Right. So we saw different name reactions, Stephen's reduction, Etard reactions, this one Rosenman reduction, right? And we saw this Grignard reagent. How is it going to have, like, how do you form ketones only from this, right? So we saw all those things last class, right? And we also ended up with this nucleophilic addition reactions. If I can show you, right? Yeah, we are talking about this nucleophilic addition reactions. Okay. Now we even saw that aldehydes are more reactive than ketones, right? Aldehydes are more reactive than ketones in this regard, right? Okay. Then we said that if I give you two different ketones or two different aldehydes, then you have to decide based on steric hindrance, right? Lesser the steric hindrance, more will be the reactivity, right? And then we saw the first reaction. This is actually a second reaction among, like, under your nucleophilic addition. The first one was actually this thing, right? Addition of Grignard reagent. Right, you're always going to form alcohols, right? So HCHO will form primary. Any other aldehyde other than formaldehyde will form secondary alcohol, and then ketone is going to form a tertiary alcohol. Right, we saw that. And then here, first, the second reaction under this is what is addition of HCN. We are always going to form something called as cyanohydrins. The carbon atom is going to have a OH, and the same carbon atom is also going to have a CN, right? And we saw what is the mechanism. First, the CN minus attacks, the C double bond O breaks, and the O minus takes up the H plus to form cyanohydrin, right? Okay. Then we went on to see this addition of alcohols, right? Now alcohols can be added like this. Now it is going to be, in this case, a neutral nucleophile, right? The lone pair on the oxygen is going to attack the carbonyl carbon, and then the C double bond O breaks, CO minus will be formed, and then the H plus transfer will happen, right? So you're going, the first step is always going to be formation of hemiacetals. What are hemiacetals? The carbon atom which is having OH and the same carbon atom having OR are what are called as hemiacetals. And if at all you use only 1:1 ratio, you're going to have hemiacetals. But if you find that the alcohol is going to be in excess, right, you are always again going to form, you're going to replace this OH also with this RO minus. That is your acetal formation will happen. OR and OR. The same carbon atom will have two OR groups, and that is going to be what is called as an acetal. Right? Hemiacetal, acetal. Okay? Right. Fine. So people, let us take some examples for this. We didn't see examples for this. Let us take some examples. Right? So if I ask you that if I have CH3CHO, right, and say I go for CH3OH, right? Can you complete this reaction? What is going to happen here? Go for the mechanism and then show me the product, people. First go for hemiacetal and then show me the acetal formation also. Right? This is an excess. Okay, if I give you, this is an excess, right? First you show me the hemiacetal, right? And then you go for acetal formation. Right? Both these things will you show? And send me in WhatsApp, people, quick. We have CH3CHO reacting with CH3OH. Take your notebooks, take your pens, and start writing. Show along with the mechanism, okay? or maybe this one I help you, the next one you do. Okay. So people, what we have here, we have this CH3, C double bond O and a H, right? Let me write it down. Okay, CH3, C double bond O with a H. Okay, now what is coming is alcohol with this CH3OH, right? Now we have the lone pair on oxygen, right? We have the lone pair on oxygen that is going to come and attack the carbon and this bond breaks, right? So what are we going to have? We are going to have CH3. I'm talking about this CH3, CO minus and a H is there. And to this carbon, what happened? This oxygen atom is attached, right? This oxygen atom is attached and that is having a hydrogen and that is also having a CH3. Done. Now what are you going to do? You are going to go for heterolytic cleavage of this particular OH bond like this. This oxygen has a positive charge here. You can understand, right? Because oxygen has lost its lone pair. Right? The oxygen has a positive charge. I don't want the positive charge. So H plus comes out and that H plus will be taken up by the O minus. Right? So you can easily form CH3COH, right? And that is attached to, and this is having a hydrogen also, and that is also having OCH. This is your acetal, sorry, hemiacetal. Right, you understand, right? The same carbon is having OH and OCH. That's a hemiacetal. Then what is going to happen, people? The same thing again. Continue this reaction with CH3OH, right? Or you can decide it as CH3O minus, right? Now that is going to come, it's a nucleophilic substitution reaction, right? That is going to come and the OH bond cleaves, right? So now what is going to happen? We are going to have CH3, CH, right? CH is there and that is having one OCH3 and that is also attached to another OCH3. Our one OCH3, another OCH3 is coming from here, the OH is replaced, right? And then you understand that this is what is going to be your acetal. Very, very simple. Addition of alcohol 2 times. First time is nucleophilic addition. Second time is going to be nucleophilic substitution. This particular reaction is actually nucleophilic substitution reaction. Is it not? Because OH minus is replaced by CH3O minus. Very, very simple. Very, very simple. All right. Okay. Now will you do this one? Right. If I give you another question, will you be able to do? Right. Say if I give you, we have CH3, C double bond O, CH3 with, say I go for C2H5OH. Right. Can you complete? Hemiacetal, acetal. Go for it. Show me the mechanism and send me in WhatsApp. Quick, people, quick. Same mechanism, except the compounds are different here, people. Go for it. We will finish it. I'll be back in a minute. Okay. I'll be back in 1 minute. People, are you doing?
1 minute.
Yeah. Okay, I got something. CH3O minus H, and this will attack, and then the CH3O minus that is going to go hemiacetal OC2H5 and OC2H5. Yeah. Okay, correct. This is Devish. Yes, Devish. Correct.
Percent.
Yeah, 1 second. Let me check. Okay, that attacks and that one breaks and the OH is taken. That is the hemiacetal. Okay, fine. Wait, 1 second. Okay, OH and OC2H5. Okay, done. And that is going to attack and the OH is gone. Right. Okay, good. That is also right. So very simple, people. Right. So again, the first step would be this coming and attacking this carbonyl carbon, and this bond breaks. And then what is going to happen? We have CH3, CO minus, CH3, and then we have this OH and C2H5, right? Then this bond breaks, right? The OH, that because oxygen is going to have a positive charge, right? And that is going to be taken up by the hydrogen. Then what you're going to have is the hemiacetal COH with one CH3, and that is going to have OC2H5. This is your hemiacetal. Right? Then what is going to happen? Then comes your another molecule of C2H5O, C2H5OH, or you can just take it as C2H5O minus. Now that is going to come and attack the carbon having the OH, and the OH bond leaves, the CO bond leaves. Right? So we are going to have CH3, CO, C2H5, CH3, and O, C2H5. This is your acetal formation. Very, very easy. Okay, right. Now, instead of using two alcohols, the two molecules of alcohol to form hemiacetal and acetal, people, right, we will be actually able to do this, right? We will be able to do this thing, right? Say, for example, what if, let me take maybe a cyclic structure. Okay, now we have the C double bond. Okay, right. Now what I'm going to do is I am going to make it react with CH2OH and CH2OH. Okay, I'm going to make it react with CH2OH. This is glycol, right? This is what is called as ethylene glycol. Okay, right, fine. This is also called as glycerol. They call it as glycerol. Okay, no issues. So now the mechanism is very simple, but the thing is that instead of having two molecules of monohydroxy compounds, we are going to use only 1 mole of this, and this itself is enough for me to go for acetal formation. Okay, but in this case, we are going to form a cyclic acetal. Let me show you this. Okay, now first step is simple. This oxygen lone pair is going to come and attack here, and this bond breaks. Right. So let me show it. Now we are going to have this O minus is going to come, and to this carbon we have this oxygen, right? And that is having a hydrogen, and that oxygen is going to have a positive charge, and that has a CH2, and that is having a CH2 and a OH. No issues. All right. Okay, now what is going to happen? The same thing, right? So this H plus leaves, and that H plus is going to be taken up by this oxygen. Okay, that's the next second step. So now what is going to happen? We would have had one OH, and we would have had one oxygen atom here, right? And that is attached to CH2, and that is also attached to one CH2 and OH. Is it correct? Yeah, right. Right. Now what is going to happen? Now say, okay, now, see people, actually, right, when you go for acetal formation, right, when you go for acetal formation, let me tell you exactly what happens. See, please understand, OH is a very bad leaving group. Okay, OH is a very bad leaving group. Okay, so for that reason, you have to convert OH into a different group so that it becomes a good leaving group. So basically, OH undergoing nucleophilic substitution is very, very rare. Okay, now what you have to do is, let me tell you like this. For example, let me take from here. Right, let me take exactly from here. Right, look at this. So we have CH3, COH, CH3, right? And then you're going to have OC2H5. Right. Now, when I go for C2H5OH is what we have actually. Okay. Now, what is going to happen is this lone pair on this oxygen is actually going to take up this H plus. One second, let me show you. Right, we have this hydrogen, right? Now, this bond goes for heterolytic cleavage, and that hydrogen is actually going to be taken up by this H plus. I mean, that OH will be taking up this H plus. So what are you eventually going to form is CH3 COH2 plus. This is what you will form. Already OH is there. One more H plus, if it gets added to this, it is going to become OH2 plus, and the other thing remains same. CH3, and we have this OC2H5. Right now, what is remaining in this? I already went for heterolytic cleavage of this. So what is remaining is C2H5O minus. Right now, we have converted OH into some other group, which actually can be a very good leaving group. Okay, so this is going to come and attack this particular carbon, and H2O leaves. Now, this is OH2 is what? Nothing but H2O, right? So we are going to have CH3, CO, C2H5, again O, C2H5, and CH3. And what is leaving out? What is leaving out is water molecule. Okay, what is leaving out is water molecule. Okay, right. This is the exact thing which is happening. We directly write C2H5O minus attacking that, and OH minus leaves. But if you look into that very carefully, it is first the H plus coming from alcohol will be taken up by this OH, right? And that is going to become OH2 plus, and then the C2H5O minus attacks. That's exactly how it should happen. Okay, right? Fine. Now, if that's the case, people, can I write it like this way? Right? I have this particular OH, I don't want this. Okay. Now this bond is going to go to heterolytic cleavage, and the hydrogen is going to be taken up by this oxygen. Right? So I will be able to write like this. We have a cyclohexyl ring, and that is having one OC2, one, okay, CH, we have this CH2, and that is attached to another CH2, and that is having now one O minus. Right now, what happened to this alcohol? This alcohol become OH2 plus. Right now, it is nucleophilic substitution, people. This will come and attack this particular carbon, and the OH2O leaves. So what are we going to have? We are going to have this one. Right. One. See, you have to understand that this oxygen attached to this carbon. Oxygen, CH2, another CH2, and this is again attached to this oxygen, and that is bonded with this carbon. Right? This is an acetal, no doubt about it, but this is an example for a cyclic acetal. Okay, now it's very, very, very simple. It might look complex, but it is very easy. Okay, whatever we did for the previous cases, that we are doing it with the help of only one alcohol, but it is having two OH groups. That's it. Okay, so this is what is called as cyclic acetal. Okay, this is what is called as cyclic acetal. Very, very simple, right? So will you do it one more time? Like if I give you another compound, will you be able to do? Right? Say we have this particular ketone, and say I'm going to make it react with CH2OH and CH2OH. Right? Do it slowly and tell me what is the cyclic acetal which is getting from. Go for it. Right, look into this very carefully.
Can I show the cyclic acetal?
Sorry, Karna.
Can I show the cyclic acetal equation?
Yeah. Like, let me show it from first. Okay, let me explain this from first so that you'll understand. Okay, so first step is very similar, right? The oxygens, one of the oxygens with lone pair is going to attack the carbon and carbon, that bond breaks, right? So you are going to form the oxygen which has lost lone pair will have a positive charge, and O minus, everything remains same. And then the H plus leaves, and that H plus will be taken up by this oxygen. Okay, now we are going to have one OH and other thing remains same, right? Okay, now what is going to happen? The CH2OH is H plus is going to leave, and that is going to be taken up by this oxygen, right? So you're going to form OH2 plus. Okay, now what is going to happen? Now the nucleophilic substitution, O minus will come and attack here, and H2O leaves, right? And that's it. You're going to form the cyclic acetal. Very, very simple. Okay, go for it, Pete. Go for it.
So there's a bond between CH2 and CH2, sir.
What, Kana?
There is a bond between CH2 and CH2.
Yeah, there is a bond. There is a bond here, oxygen, and there is a bond here to this oxygen, and that is attached to the CH2, and this is attached to the CH2, and again, these two are attached. You can understand this. These two are attached.
Okay.
Right? Guys, I'm actually thinking, since we have a lot of courses to cover in a very short amount of time, we have class generally on Fridays, right? Friday and Sunday. Can we make Friday classes to be 2 hours class? Are you guys okay with it? So we will have it from 5 to 7 we'll have, but obviously I'll give you a break in between. After 1 hour, I'll give you a break of 10 minutes or 15 minutes, and then we can again continue. Is it okay for you guys? Friday having 2 hours, not only for next class, for all the upcoming classes. Friday will be 2 hours.
Yes, that's fine.
Okay, let me talk to Raghav. Let me see what he tells. Saturday and Sunday it's not possible, because again after this I have your 11th, I have your juniors classes, right? So that cannot be extended. Already for 11th, both the classes are happening for 2 hours. They are having classes on Saturdays and Sundays, right? Saturday 2 hours class, Sunday also they have 2 hours class, right? We will see what maximum we can do for you. Sent. Okay, 1 second.
But I don't know how to name the structures.
So we have this one attacking that. Okay, OH2 done. So we have OH in this, and then OH2 plus. Yeah. Okay. There and there, very, very small mistakes are there. Let me show it to you. Yeah, correct. What I've done is correct.
So can you say how to name the structure also?
How to name the structure? Don't worry. No, don't worry about the naming of structures. Don't worry. You just have to understand this is going to be cyclic acetal. Right? Don't worry about it. Anybody else wants to send me? Maybe I'll give you 1 more minute. See, the thing about organic chemistry is when I tell you, and that moment only you practice, you'll be able to understand. Okay. But tomorrow I ask you the same mechanism. I don't give you this PDF or whatever it is, right? You might or might not be able to do this, right? So the thing about organic chemistry is that you have to be in constant touch. Constant touch you have to be in. Okay. So this is Devesh, I guess, right? Yeah. 1 second, Devesh. Let me check. Okay. You have to show the lone pair. Fine, no issues. So we have O minus. Oxygen should have a positive charge in the second step. Saying so then, okay, that H plus you have already put it here, and that is going to be taken OH2 plus, and yeah, correct, right? Everything is correct. Eventually, the product is also correct, but mechanism little there and there, small problems. Okay, let me show it to you people, right? So you have to show the lone pair here, and then that lone pair should be attacking this particular carbonyl carbon, and that bond breaks first. Okay, then what is going to happen? We have one O minus, and we have oxygen having hydrogen, which is having a positive charge, CH2. Let me rub the cyclic acetal part. Okay, now that is having a CH2, and that is having another CH2, and that is having O and a H. No issues, right? Then it is very simple. The first step, the next step would be removal of this H plus, and this O minus comes and takes up the H plus, right? So now what we have is one OH, and the same carbon atom is having O, CH2, and that is having one OH. Very simple. Right now, what is going to happen? Now, this bond goes for heterolytic cleavage, this bond, and that oxygen lone pair is going to go and take up the H plus, right? So then what we have is we have the OH2 plus. You have to show that this is the bond, right? The carbon atom should be attached to oxygen atom, OH2 plus, and then what we have is oxygen, CH2, another CH2, and I'm having one O minus. Right, then it is very simple. Then make this come and attack this particular carbon, and this bond goes for heterolytic cleavage. H2O is cleaved, right? So what are we going to have? Okay, we have one oxygen like this, right? Already one oxygen coming and attacking here, this oxygen, right? And there is another oxygen like this and attached with CH2, and a bond. And obviously the side product is going to be water molecule. This is the final product. Okay. Very simple. Very simple. Okay, people. Now, what is the speciality of this? Like, even though you might or might not even use this particular thing, but there is a thing, right? There is a usefulness for this particular cyclic acetal which I'm forming. Okay. Now, what you have to understand is, like, let me give you a case, right? See, I have CH2, C double bond O, and a CH3. Okay, right. Now, for example, say I go for one molecule of HCl, right? One molecule of HCl. Now, this is an aldehyde. This is a ketone, which will react. If I put only one molecule of HCl, the Cn minus will attack this carbon, say carbon number 1 or carbon number 3. Which carbon it will attack? I have an aldehyde and a ketone, the same molecule, and I'm going for Cn minus. Which carbon the Cn minus will attack? Carbon number 1 or carbon number 3? Okay, people, let us go for the guess game. Go to your chat box and put your answers. 1 or 3. It's just a guess game. You need not be right. You need not be wrong. Just go for it. Write carbon number 1 or 1 or 2. Sorry, 1 or 3. This is 3. Okay, just go for it and tell me. Right? Just put it in the chat box. 1 or 3. Go on, people. right? We have carbon number 1 and carbon number 3. I am putting only one molecule of HCN. Okay, not two molecules, only one molecule of HCN, right? And I'm going for attacking the carbonyl carbon. There are two carbonyl carbons here. This is one carbonyl carbon, another carbonyl carbon. Which one it will attack? You need not be right, you need not be wrong. Just go for the chat box and put the answers, people. 1 or 3. Okay, 1, 1. Okay, fine. Go on, everybody participate. We have almost 13 guys of you. Carbon number 1. Seshank says also carbon number 1. Okay, okay. Fine. Next. Yeah, and it says 1. Okay. Anybody else wants to contribute? Okay, fine. Right. Fine, 1 is correct, right? It is going to be the aldehyde, or say the carbon number 1, which is actually going to be taken up the CN minus, right? But why? Why is it like this, people? Any idea? Why only aldehyde will react and not the ketone? Why? What kind of reaction is this, people? What kind of nucleophilic what?
Substitution.
Is it substitution?
Addition, sir. Nucleophilic.
Nucleophilic addition reaction, right? So when we have nucleophilic addition reactions, we have already done this, right? We have already done the reactivity of aldehydes and ketones. We know that aldehydes are going to be more reactive with respect to this nucleophilic addition reactions, right? So if at all you don't do anything and then you put the HCN, you will see that the molecule, the product would have been CH, OH, CN, CH2, C double bond O, CH3. This was what would have been the product. Mechanism is very simple. You can go attack CN minus, O minus breaks, takes up the H plus to form the cyanohydrin, right? But I want the product only to be like this. C, OH and CN like this. I want this product only. Okay, I want this product only, right? What should I do? Obviously, it's naturally understood that the aldehydes are going to be more reactive than the corresponding ketones. So definitely this is the product I expected. But what I want, right, in the laboratory, I want to do something with this only. Okay, now what should I do? In these cases only, people, you are going to have the acetal or say cyclic acetal formation to be very, 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 very helpful. Okay, now before we go on to this, let me tell you one point. Okay, now whether it's an acetal or a hemiacetal, okay, now when you go for acidic hydrolysis, when you go for H plus in the presence of H2O, you are going to get back your aldehyde or ketone, right? Whether it's from hemiacetal or acetal or cyclic acetal, whatever you have, if you go for hydrolysis in the acidic medium, you are going to get back whatever you initially had. This is what you initially had, this compound, right? You are going to get back that. Okay, so it is very simple for us to retrieve back whatever was the aldehyde or ketone we had initially. Okay, so what I'm going to do is if I want only this product and not this, right, what should I do? Let me see, right? So we have this C double bond O with the H, right? CH2, C double bond O, C double bond O, and a CH3. We have this compound with us. Okay. Now, when I go for say CH2OH and CH2OH, again, this is an example for a nucleophilic addition reaction only. The addition of alcohol, it is again a nucleophilic addition only. Definitely, again, it is going to be only this carbon which is going to be taken up, which is going to take up this particular glycol, that is CH2OH and CH2OH, right? I don't want to show the mechanism. I can directly show what would have been the acetal, right? So we would have formed O, CH2, CH2, and a O. Done. This would have been the cyclic acetal, and it has a hydrogen also. No issues. This has a hydrogen also. The other thing remains same. CH2, C double bond O, CH3. Okay. Now what I do is now I go for HCN addition. Okay. Now obviously this carbon cannot be taking up any more CN minus because that is not a C double bond O anymore. right? So from this, if Cn minus comes, it has no other choice than to go and attack this particular carbon. Okay, so now what is going to happen? We have this CH, right? O, CH2, CH2, again this one, right? And then we have the CH2, CO minus. Let me write directly the product. CO minus will be there. It is take up the H plus, OH, Cn, and CH3. Right now, I want what? I want this to be the product. So what should I do? I should go for what? I should go for acidic hydrolysis of this one. So what I'm going to get? This entire thing is going to convert itself into an aldehyde. So CHO, CH2, COH, Cn, CH3. Right? This is how it is very useful. Okay. Now these kind of things are what are called as protecting groups. Right? These kind of groups are what are called as protecting group. There are two functional groups in the molecule, but I want only one of the functional group to react. I don't want the other one to react. So what I do, whichever I don't want it to react, I protect it. Protect it means what? You convert that into something else. Say in this case, I don't want this to react, so I protect it with this glycol, so that the acetal formation happens, and then you do whatever the reaction you want, HCN or whatever reaction you want, that is going to happen, and then you this step is what is called as your deprotection step. Right? In the deprotection step, whatever was protected, now that is going to go back to its original position. Okay, now don't worry, you are not going to use any of this in your exams or your school exams, nothing you're going to use, but I'm telling you, this is how you do something in the lab. This is how you do organic chemistry in the lab. Right? Okay, right? So this is a small point I wanted to tell you. Right? Okay, so people, that is about your acetals and hemiacetal formation. Anybody has any questions you want to ask me? Okay, fine. So that is about your acetals and hemiacetals, right? Fine. So is there any other nucleophilic addition reaction you can have? Yes, we can have. Going to that. Okay. Now, I don't know. This is, I think, the third one under nucleophilic addition. Addition of NaHSO3. Right? This is your sodium bisulfite. Okay. Sodium bisulfite. Okay, very simple, people, very simple. So now you understand that this will be able to dissociate as Na plus and SHO3 minus, isn't it? Now if you check how exactly is the structure of this SHO3 minus is what is called as your bisulfite ITE ion. Sulfate is different. Sulfate is SO4 2 minus. This is fate, right? And we have something called as SO3 2 minus, that is sulfide, right? Now, if I had one hydrogen to this, right? If I say that I'm going to have HSO4 minus, right? That is going to be bisulfate, right? And if I add one H to this, if it is going to become HSO3 minus, then that is going to become bisulfite. Okay, right. So we are going for addition of sodium bisulfite to the carbonyl compound. Okay, again, still it is going to be nucleophilic addition reactions only, people, right? So okay, now let us look at the structure of this HSO3 minus. So we have one S double bond O, right? And then we have one OH, right? And we have one O minus. Okay, we have one O minus. Okay, right. So please understand, it is going to be this oxygen which is going to go and attack the carbonyl carbon. Okay, this is the O minus, that is the nucleophile, that only will go and attack the carbonyl carbon, right? So we have this C double bond O, that is the carbonyl compound, either an aldehyde or a ketone, doesn't matter. Okay, now this will go on. Oh, sorry. Okay, right? So this will go and attack the carbonyl carbon, and the bond breaks. Very simple, right? So now what we are, this is what is wrong. Okay, let me start from first. So we have this C double bond O. Okay, now we know the structure of SSO3 minus, sulfur with double bond O with one OH and one O minus. And I told you this is the nucleophile that is going to go and attack this carbonyl carbon, and obviously this bond breaks. Okay. Now what are we going to have? We are going to have CO minus, 2 more bonds, and we have this oxygen with, let me write it as OSO2H. Okay, that is understood. That is CS, 2 oxygens and 1 H. Let me write it like this only, no issues. Okay, right. Now what are you going to have is, you understand that this O minus is there, right? That can take up a H plus. That can take up a H plus, right? Now that is going to be taking up the H plus, or actually this is not H plus, right? So now we understand that there is already Na plus in the solution, right? There is already the sodium bisulfite, Na plus ion is already there. So you can write O minus Na plus, O minus Na plus. Okay, now what are we going to do is, now let me actually show you the structure itself here, right? So we have S double bond O, and that was having a OH, right? So now what is going to happen is, we are going to transfer Na plus and H plus. We are going to replace both of them in the opposite positions. Okay, Na plus is going to come to this oxygen and H plus is going to go to this oxygen. Okay, that will happen, right? So now if that happens, we have COH, no issues, and then we have the other 2 bonds, and we have this O, SO3, SO2, Na, SO2 minus, Na plus. This is what we have. Okay, now why are we even studying about this is because this is going to be a white precipitator, right? This is going to be a white precipitator, very important. Right? When you go for the bisulfite addition, the product formed is actually going to be a white precipitate. Okay. Now, so this particular bisulfite addition, this particular reaction, addition of sodium bisulfite can be a test for carbonyl compounds. Right? It can be a test for carbonyl compounds. Okay, why? Because if at all I'm going to have a carbonyl compound, that a bisulfite addition reaction takes place and you are going to form a white precipitator, right? So if I give you an alcohol in one test tube, haloalkane in another test tube, and an aldehyde in another test tube, you add one test tube, you are in all the test tubes, you had sodium bisulfite, whichever test tube you are forming the white precipitate, that test tube contains your aldehyde or ketone, right? So like this, you will be able to use this bisulfite addition for test for carbonyl compounds. Both aldehyde and ketone, both will give this test. No issues at all. Okay, right? So if I have to take a specific example, right? So let me take CH3, C double bond O with a H, right? And I'm going for NaSHO3, right? You can show the mechanism, all these things you can show it, right? Eventually what is going to happen? We are going to have COH, and already I have a H, and that is going to be OSO2 minus Na plus. Again, this will be a white precipitator. Right? Let me show you the mechanism also. At least 2 times you have to show the mechanism so that you will get into your head. So C double bond O is there, H is there. Now what comes is this S double bond O minus Na plus is there. Right, and we have this OH also, and this O minus is the one who's going to come and attack here. This bond breaks. Then what is going to happen is CH3, CO minus, and we have the Na plus also. Okay, and then I have this oxygen. I'm talking about this oxygen that is having a CS double bond O, and that is having a OH. Now what are we going to do? We are going to replace this Na plus and H plus. Right, so we are going to have CH3, CO, we have a H also, CH, let me write, there is a H here, okay, CH3CHO, H, I have a OH, and what I have this O, S double bond O minus Na plus, right, that is what is written here, same thing, right, and this is nothing but a white precipitator. Okay, so this can be done for any carbonyl compound, any carbonyl. All right, so that is the next example for nucleophilic addition reaction, bisulfite addition. Easy, right? So they will not ask you much questions in this. They will just tell you maybe in the form of a test or in the form of this white precipitate, something questions can come. Okay, right? So that is about your bisulfite addition. Moving on, right? The next nucleophilic addition you're talking about is the fourth one, I guess, right? That is addition of ammonia derivatives. Ammonia derivatives. Okay, guys, just give me one moment. I'll be back. Just give me one moment. Okay, right. So I was telling that the next what is the nucleophilic addition reaction is addition of ammonia derivatives. Okay, now we know what is ammonia, right? Ammonia is NH3. Okay, now if I replace ammonia with any, if I replace the hydrogens of ammonia with say something else, for example, this is ammonia, right? Now if I replace say one of the hydrogen atom with the OH2, right? Now that is going to become hydroxyl amine. That is what is called as hydroxyl amine, right? Now say I replace one of the hydrogens with an alkyl group, say R, NH2R, right? Now this is going to become a primary amine. That is what you're going to study in the next chapters, amines chapter, right? There's again a separate chapter for all these. Now why should that only one hydrogen is replaced? I can go for two hydrogen getting replaced, right? So only one hydrogen I have and two alkyl groups like this, that is going to become secondary, right? Now another thing can be, say I can replace it with this one CONH2, one hydrogen, three hydrogen should be there. One of the hydrogens replaced with the CONH2. This is nothing but your urea, right? Now also I can have say NH2, one of the hydrogen, NH3 should be there. One hydrogen replaced with one other NH2 group, right? Now this is what is called as hydrazine, right? So what you understand is we are going to have this particular addition reactions happening, right? The addition of these kind of derivatives. So many things we will have, and I'll tell you one by one everything will try to understand. Okay, right? So now let us try to understand how exactly ammonia is actually going to have this kind of first, if you understand how ammonia reacts with your C double bond O's, then all the other things are going to be very, very similar. Okay, so we are going to add this ammonia or its ammonia derivatives to the carbonyl compounds. Okay, so let us try to understand. So we have this C double bond O people. Okay, now say let me take ammonia. Okay, right? Now the same thing will happen. The ammonia as a lone pair, it is going to go and attack this carbonyl carbon, and this bond breaks. Again, a nucleophilic addition reaction only. So what we'll have, we will have CO minus, two more bonds with NH3 plus. Okay, NH3 plus. Now I don't want this NH3. I don't want this particular nitrogen to have a positive charge. Let me write it like this for you. Right. So let me write this as NH2H. Okay. Now what I can do is I can break this heterolytically and give the electron to nitrogen, and this O minus can come and take up the hydrogen now. Right. H plus it can take. So what are we going to have? We are going to have C O H, and we are going to have one NH2. Is it not? NH2 is there, hydrogen is lost, and that is taken up by this oxygen. Very simple. Now people, there are certain times you will see that the compound is going to become unstable. Okay, right. Now, what are all the cases where the compound can become unstable is I think we have already seen this. Whenever, say, there are two carbon atom which is having two OH groups, right? Or say the carbon atom is having one OH group and one NH2 group, right? Or obviously, okay, these two are enough for us. Okay. Now, whenever you have these kind of cases, right? Whenever you have these kind of cases, those kind of molecules are very, very unstable. Okay. Now, why is it unstable? Is because you understand that these oxygen atoms have lone pair, lone pair, lone pair, lone pair. Everything has a lone pair now, isn't it? So, because of the lone pair repulsions, right? Because of lone pair repulsions, right? They are highly unstable. Highly unstable. Okay, fine. If they are formed, then what we should do? If they are unstable, something has to happen, right? Right. So remember, people, whenever you can have two OH groups like this, the moment you see that, you remove one water molecule, H from this, OH from this, right? Then if you remove H2O, what is going to happen? There are two bonds for carbon, right? Two bonds, two OH groups for carbon. Now you have removed one OH, so you make a double bond with oxygen. That's it. There is only one oxygen atom remaining, right? So you make it into a carbonyl compound. Okay, you make it into a carbonyl compound. Very, very simple. Very, very simple. Okay, so the moment you see two OH of the same carbon atom, you are going to remove a water molecule minus H2O, and you are going to form the carbonyl compound, right? And the same thing will be applicable for these kind of compounds also. Again, from this you remove one water molecule. But how are you going to remove the water molecule? Let me tell you. Right. So let me write this one as NH2H. Right. Now you are going to remove the water molecule like this. Okay. OH and H. Right. Now you are going to make a double bond, obviously, between carbon and hydrogen in this case. That's the only difference. So we are going to have C double bond NH like this. Okay, C double bond NH like this. Okay. Right. So whenever you have two OH to the same carbon atom, or say one OH group and one NH2 group on the same carbon atom, that is going to be very, 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 very highly unstable because of lone pair repulsions. So the moment you form them, what are you going to do? You are going to remove one water molecule to form either the carbonyl compound or these kind of compounds are what are called as imines. Okay, these kind of, whenever you have the C double bond N, right, that is those kind of compounds are what are called as imines. So either you go for a carbonyl compound or you form an imine. Okay, now the same scenario is only here, right? We have one OH and NH2 on the same carbon atom, is it not? So I can easily remove one water molecule. We have this H, so we can easily remove this H2O molecule to form what? To form C. There are two more bonds, and I have a double bond with this NH. That's it. Okay, this will be the product. This will be the product of all the things. Okay, so first step is very similar. First step is ammonia attacking as a nucleophile. The C bond or double bond O breaks. So we form this O minus and NH2 plus, NH3 plus actually. Okay, now from this what I did, I transferred the H plus from the nitrogen to the oxygen. So you form this kind of compounds, and I told you these are unstable. The moment you form them OH, H, you remove water molecule minus H2O to form these kind of compounds. Okay, right? So this is what is going to happen for any ammonia derivative for that matter. Okay, right? So if at all you don't want to understand the mechanism, also there is going to be a shortcut. Okay, I'm going to give you a shortcut. Okay, right? So people, right? So any ammonia derivative, right? Any ammonia derivative can be represented like this: NH2Z. Right? So obviously I told you one of the hydrogen of ammonia is replaced with some other group, and that group is Z. Say for example, if that group is OH, then that is going to be called as hydroxyl amine. If that group is going to be an alkyl group, it is going to be called as primary amine. This will not work. Okay, this will see later secondary amine. And say the hydrogen atom is replaced by one NH2 group, it is going to be called as hydrazine. If the hydrogen atom is replaced by the CONH2, it is going to be called as urea. Right? So we will be able to represent these ammonia derivatives like this: NH2Z. Okay, right? So now if I have this C double bond O, okay, reacting with NH2Z, right? Let me write it like this, H2NZ. Okay, now the shortcut coming for you. Now what I'm going to do is remove water molecule. Now, H2 and O. So remove this. So what is going to happen now? The carbon and the nitrogen is going to have one, what is that? They're going to have a form of a double bond, right? So we have C double bond N is it. This is the product. Okay, so mechanism also you understood, a very, very simple mechanism, right? And then you understand that we are going to have this kind of shortcut also. We have the C double bond O, NH2Z, right? The ammonia derivative or ammonia, this can be H also, doesn't matter, right? So what are you going to do? You are going to remove one water molecule H2 from N and oxygen from the carbonyl compound, and you are going to form the final product. Okay, right? Fine. So let us understand like what are the different types of ammonia derivatives and what not can be the products we can form. What is the name of the product we can form? Okay, right. So let us take this, right? So we will take fine. So first, let me give it a form of a table, guys. Can you just go to your textbook, right? Can you just go to your textbook, and I don't know which page number or not it is there, but you will see that addition of ammonia derivatives will be there, and they would have given you a table, right? Can someone just click a picture and send it to me in WhatsApp so that that'll be helpful for us, or let me check in internet itself. Wait. Not required. Wait, I'll check in internet itself. I need a table. Anybody has a table? Please give me one. Oops, what happened? Yeah, this is exactly what I'm looking for. Right. So let me Control C this. Let me see if I can mark it here. Not like this, not like this. Wait, guys, just a moment. Copy image.
So I've sent it in WhatsApp.
Yeah, I got this here, no issues. Okay, I hope everybody is able to see this. Okay, right. Now, people, if at all you check the first one, right, we're adding just ammonia. That means what? I told you NH2Z. Okay, now, and sorry, NH2Z. Now they're telling that the Z is H itself. That is ammonia. Okay, now this thing is very simple, people. Anything what are you going to do? You are just going to remove water molecule and get the answer. Now, this is not very simple now, right? Say if I, for example, take ammonia, we have this C double bond O, right? And we have the ammonia. Let me write it as H2NH like this. Now, what are you going to do? You're going to remove the water molecule to form C double bond NH. And that's exactly what is formed here. And that product name is what is called as imine. Okay, right. Now, if the Z is R, that means that I'm talking about the second one. If the Z is R, so we have this C double bond O, and what are we going to do? We are going to make it react with NH2R. Again, the same thing. We are going to have C double bond N R, and these kind of compounds are what are called as substituted imines. Normal, if at all you have only hydrogen, it is called amine. But if at all you have a carbon here, that is going to be called as substituted amine, and it is very important, Schiff's base. It is also called as Schiff's base. Okay, right? Next, what we have next is OH, right? Next is OH we have. That means what? Z is OH now. So C double bond O with H2NOH. Now the Z is OH. Again, same thing, H2O molecule removed. So we are going to have C double bond NOH. This see, the names are very important. Okay, this NH2OH is what is called as hydroxyl amine, whereas this one is what is going to be called as an oxime. Very important. The C double bond NOH is what is called as an oxime. You can see the name. Okay, right. Next, like that, we have the Z now to be NH2, right? N, okay, I'll write it as H2 and NH2, like this. Again, same thing, removal of water molecule to form C double bond NH2. Now this compound is what is called as hydrazine, and this compound is what is called as hydrazone, right? You can check the name here, right? This is hydrazine, NH2 is called as hydrazine, and this one is going to be called as a hydrazone. The product is what is called as a hydrazone, right? Next comes what? Next comes phenylhydrazine. What is phenylhydrazine? Is very simple, people. Now what we have is this C double bond O plus we have this H2N. Now the Z is going to be NH. Now again, if it is NH2, it is hydrazine. I remove one more hydrogen from this and I go for one phenyl, like this. Okay, this thing is very simple. The product is very simple. All that you have to understand is the name. This one is what is called as phenylhydrazine, right? And obviously the product is going to be C double bond N. Again, I have this NH, and that is attached to this benzene ring. Okay, now this is obviously going to be called as phenylhydrazone, right? And that's exactly what is written here, right? Now this and this are almost similar, but except that in the benzene ring we are going to have two NO2 groups. That's why it is called as. Now you understand, right? This is second question. 1, 2, 3, 4. Right? So 2, 4 dinitrophenylhydrazine, we call it 2, 4 dinitrophenylhydrazine. Again, the same thing will come, except that you're going to put two NO2 groups in the second and fourth position, right? And at last, we have something called a semicarbazide. Now again, that's very simple, people. What is semicarbazide? We have the C double bond O. Now we have this H2N. Okay, now Z, look at the Z. Z is going to be NHCONH2. Okay, this is the entire thing is your Z. Okay, and this entire thing is what is called as semicarbazide. Okay, now the product is very similar. To have this H2O removed, and then what you have, we have the C double bond N, NH, C double bond O, NH2. Okay, so we understand that this particular compound name is what is called as semicarbazone, azide to semicarbazone, right? And that's exactly what is written here also. Okay, right? So very, very, very simple. All that you have to understand is what is the Z, what is the reagent name, and what is the product name. That has to be there in your fingertips. And obviously the product. What is the product? What is the product? Structure. Product's structure and the product's name. Everything should be there in your fingertips. Okay, so this is what is about addition of ammonia derivatives. I told you, very, very simple. Very, very simple. Anybody has any questions here? Anybody wants to ask me anything? Mechanism.
All the compound Z is the only thing that's different, sir.
Sorry?
In all the compound, only Z is the difference.
Only Z is?
The difference between all compounds. Like Z is different for each compound, only Z is different.
Yeah, each compound only Z is different. Yes, nothing else is different. Mechanism is same. How you form the product is same. Everything is same, only Z is different. Yes, correct.
So that means you have to remember only how the formation of Z, sir, like the structure of Z alone.
Yeah, no, that's what. If you remember the Z, right, I told you, this is the general structure. I'm sorry, this one, right? This is the general structure, C double bond N Z. So if you can remember what is Z and the name of the product, that is enough. That's it. Different Zs, different products. That's it. Yes, understood?
Yes, I understood.
Okay, good. Right, people? And the mechanism is very similar. Again, instead of this, we can write it as NH2Z, and eventually you are going to form what? In this case, you are going to form C double bond NZ. That's it. The mechanism is very simple. First addition of the nucleophile, CO minus, and then you understand that the OH and the nitrogen compound cannot be there in the same carbon. Remove the water molecule. Eventually, this is the product. Okay, so we understood the mechanism also, the shortcut also, and the different Zs along with their names and the product steps. Right, everything should be there in your fingertips. Okay, right. So that is about your addition of ammonia derivatives. Right, and with this, all the nucleophilic addition reactions are done. Right, so first, so if I can just summarize to you, right, what are all the different nucleophilic addition reactions? Right, first one was addition reaction with Grignard reagent. Second one was with HCN. Third one was with alcohols, right? And fourth one was with this thing. What is that? Sodium bisulfite, NaHSO3. And the fifth one was ammonia derivatives, NH2Z. Okay, so these are all the different nucleophilic addition reactions you can have along with your carbonyl compounds. Okay, right, fine. So that is about your different nucleophilic addition reactions, right? So we completed one beautiful class of reactions, right? So now what we'll do is we will now go for another class of reactions called as reduction. Did we already see reduction, people? Did we see reduction before itself? Did we see reduction of carbonyl compounds? Did we see? No? Okay, fine. So people, right? So we have to understand what are all the different reducing agents first. Okay, right. Now reducing agents, only 3 or 4 things, if you remember, that is more than enough. Okay, now again, I can have strong reducing agents and I can have weak reducing agents. But in this case, that doesn't matter. Whether you use strong reducing agent or a weak reducing agent, it really doesn't matter here. Okay, fine. Anyways, I'll tell you. Strong reducing agent, one of the most important ones is LiAlH4, lithium aluminium hydride. Okay, and the other one you can remember is H2 in the presence of nickel or palladium or platinum, whatever. That is again that thing. And in weak reducing agent, you remember only one thing, that is NaBH4, sodium borohydride. Okay, remember the names also, people. Sometimes in the question, they will not give you the formula. They might give you the names. Sodium borohydride. Okay, and this one is what is called as lithium aluminium hydride. Okay, right. Now, whatever be the things, whatever be the reducing agent, whether it's strong or weak, in this case, whenever you go for reduction of carbonyl compounds, whether that is whenever you go for reduction of aldehydes or ketones, whether you use strong or weak, it really doesn't matter. Okay, because both of them are going to give you the same product. All right. Okay. Now, what is going to happen? Let us see. Right. So, people, whenever we have an aldehyde, right, whenever we have an aldehyde, and we go for a reduction of this, whether it's strong reducing agent or a weak reducing agent, we are always going to get primary alcohols. You have already studied this in alcohols, right? And whenever we have ketones on reduction, right, that is going to give us secondary alcohols. That's it. This is all that we have to understand. Okay, right? Fine. Now let us take some examples, right? Say, let me have CH3, CHO. Now say I go for H2 in the presence of nickel. What is going to happen? This entire thing, CHO, is now getting converted into alcohol, CH3, CH2, OH. Right? Now say I have another, say, ketone, for example, like this, and say I go for LiAlH4. Now what is going to happen? That ketone is now getting converted into alcohol. Now this secondary alcohol, you can understand. This is primary alcohol, you can see. right? Say another case we can take. Okay, we have another ketone like this. Say I go for NaBH4. Again, that particular ketone is now getting converted into OH. Again, a secondary alcohol. Right? This is what we need to know. Okay, and there is one special thing about LiAlH4 and NaBH4. Okay, this LiAlH4 and NaBH4 is actually very special, right? Why are they special? We'll try to understand. Okay, now for example, let us take this, right? Okay, we have the C double bond O and there's a double bond here. C double bond C is there, and say I go for LiAlH4 or NaBH4, doesn't matter. Both of them are going to react in the same way. Okay, and this same compound, I am going to make it react with hydrogen of nickel, hydrogenation. Okay, now the speciality of LiAlH4 and NaBH4 is that LiAlH4 or NaBH4, right? It does not affect C double bond Cs or C triple bond Cs for that matter. Okay, whenever you have olefinic bonds, these are what the C double bond C or C triple bond Cs, these are what are called as olefinic bonds. Olefinic bonds are nothing but C double bonds. These are C triple bond Cs. So your LiAlH4 or NaBH4 will not affect your C double bond Cs or C triple bond Cs. Okay, so if at all you go for a reducing agent like this, so the double bond stays as such. There is nothing getting affected. Okay, but the ketone or an aldehyde, that alone will be converted into alcohol, right? But we know that H2 bar nickel is actually used for hydrogenation of C double bond Cs and C triple bond Cs, right? So if you do this, right, the double bond is also gone and the ketone is also reduced to the alcohol. You have to be very careful with this, right? If you use LiAlH4 or NaBH4, the double bond is not getting affected. But if you use H2 bar nickel, both double bond as well as the carbonyl compound both undergoes reduction. Okay, we have to be very, very careful with this. All right. So that is about the reduction part also. Very, very simple. Very, very easy. Right? But now, people, we have to understand what is the H2 bar nickel mechanism you don't have to worry about. But LiAlH4 or NaBH4 mechanism is little important. Like even though it is not given in a textbook, but you can know this. Okay, very, very simple. Right? So what is going to happen is, let me take some normal thing, C double bond O with one CH3. Now say I go for LiAlH4 or NaBH4. Both of them will have the same mechanism. Okay. Now from the name itself, you can understand, right? This is a hydride, lithium, aluminum hydride. So from this, what comes is H minus. Okay. From this, what comes is H minus. Okay, now I can tell this is also an example for a nucleophilic addition because it is going to be this H minus coming and attacking this carbonyl carbon and the C double bond O breaks. Okay, right? Then what is going to happen? CH3, CO minus with a H with one CH3. Right? Now, obviously, this will take up a H plus from the water molecule. Obviously, this will be dissolved in water, right? This will be dissolved in water. From the water, I can take up a H plus to form CH3, CH, OH, CH3. That is the mechanism. Whether it is NaBH4 or LiAlH4, they are going to produce these hydrides, and those hydrides as nucleophiles are going to go and attack the carbonyl carbon, thereby converting them into the corresponding alcohols. Very, very easy. Okay, right? So I think we'll stop with this for today. Okay, right? And then we'll see the other things in the next class. Right? Reduction part is over. Now we are almost, maybe next week I should be completing this chapter. Okay, I think next week by Saturday itself, I should be completing this chapter. If at all we have 2 hours, we will try to complete this chapter, but we have to solve a lot of questions. Lot of questions are there to solve. Okay, right? And we'll solve a lot of questions also.
So could you explain again that H minus and H2?
Yeah, right. So we have this CH3, C double bond O, CH3, right? Now from LiAlH4 or NaBH4, it's a hydride. I know what is the hydride ion, right? I have H minus with 2 electrons. So that is going to come and attack, and this bond breaks. Okay, right. Now what is going to happen? The same thing, nucleophilic addition reaction only. CO minus will be formed because that bond breaks, and to this carbon, what is attached now? Hydrogen is attached. And then other thing remains same. Now what is going to happen? We are going to have a H plus coming from where? Coming from water. Okay. Now that is going to take up the O, the O minus is going to take up the H plus to form OH, and the H remains same, and we have this. That is what is going to happen.
Okay, sir. Understood.
Understood, right? Anybody else has any other questions to ask me?
No, sir.
Okay, fine, people, right? We'll wind up for today, right? We'll meet next week, and then I'll be able to I'll try to complete the chapter next week along with the questions. Maybe Saturday we'll complete it, and Sunday exclusively we'll have only for questions, how to solve questions, how to do conversions, how to do distinguishing, how to do answer some theoretical questions. All those things we'll try to understand. Okay, right? Fine, people. Let me stop right here. Okay, and thank you so much. We'll meet again next week.
Thank you, sir.
Thank you. Thank you, everybody.
Thank you.
Yeah.